There is a particular kind of silence that exists at the edges of things, at the boundary where the familiar ends and the unknown begins, where the last traces of something recognizable slowly dissolve into a darkness so vast and so patient that it seems to breathe. It is in this silence that the most extraordinary visitors arrive, not with noise, not with announcement, not with any signal that we were prepared to receive, but with light, a faint, cold, ancient light that reaches our telescopes after a journey so incomprehensibly long that the word journey itself begins to feel inadequate. The universe does not hurry. It does not need to. And the objects it sends across the interstellar dark travel with the same unhurried certainty, carrying within their frozen cores the chemistry of worlds we have never seen, the remnants of stars we will never visit, the raw material of stories that began long before our own sun ignited its first nuclear fires, deep in the heart of a collapsing cloud of gas and dust. This is the story of one such visitor, a comet that came not from the cold outer reservoirs of our own solar system, not from the distant spherical shell of icy bodies we call the Oort Cloud, nor from the flattened disk of frozen debris beyond Neptune that we know as the Kuiper Belt, but from somewhere else entirely, from another star, from another system, from a place so remote that the light traveling from it at the speed of light would take years, perhaps decades, perhaps centuries to reach us. And yet this small, tumbling, outgassing object made the crossing not at the speed of light, but at the speed of something much slower, something physical and real and ancient, drifting through the interstellar medium with the patient indifference of a traveler who has forgotten the destination and remembers only the motion. To understand why the arrival of this object mattered so deeply, why astronomers around the world paused in the middle of their routines and looked again at the data, checked their calculations, I ran the numbers a second time, and then a third. You must first understand something about the nature of our solar system and the assumptions we had quietly built into the architecture of our expectations. For a very long time, centuries even, the working assumption among astronomers and planetary scientists was that comets were local, that they were ours, that every icy body streaking through the inner solar system on a long, elliptical orbit had originated somewhere within the gravitational family of our own sun, perhaps flung inward from the Oort Cloud by the subtle gravitational nudge of a passing star, or perturbed from the Kuiper Belt by the slow gravitational choreography of the giant outer planets. This assumption was not unreasonable. It was, in fact, supported by every comet ever observed until a certain autumn morning in 2019, when everything changed. But to arrive at that morning, we must first travel backward not just in time, but in concept, and sit for a moment with the question of what a comet actually is, because the word itself carries so much cultural weight, so much mythology and superstition and awe, that it is easy to forget what lies beneath the drama. A comet is, at its most fundamental, a small body composed of ice, dust, and rocky material, a remnant fragment from the formation of a planetary system, a piece of the original building material that was never incorporated into a planet or a moon or a larger body, left instead to wander in the cold darkness at the system's edge. When a comet is far from its star, it is quiet, a dark, irregular lump of frozen gases and silicate grains, invisible to all but the most powerful telescopes, carrying its frozen chemistry in a kind of deep dormancy. But when it falls inward, when the warmth of a star begins to reach it, something remarkable happens. The ices begin to sublimate, to transform directly from solid to gas, without passing through a liquid state. And as those gases stream away from the nucleus, they carry with them clouds of dust, and those clouds catch the sunlight, and suddenly what was invisible becomes luminous. The coma forms a diffuse envelope of gas and dust surrounding the nucleus. The tail stretches outward, always pointing away from the sun, pushed by the solar wind and radiation pressure, sometimes stretching for tens of millions of kilometers across the sky. A comet announces itself. It becomes visible, and in that visibility, it reveals its chemistry, the specific molecules embedded in its ices, the ratios of isotopes frozen within it, the fingerprints of the conditions under which it formed, readable by spectrographs, the way a physician reads a diagnostic scan. The comets of our own solar system have been studied for centuries, and in recent decades with extraordinary precision. The European Space Agency's Rosetta mission, which orbited Comet 67P Churyumov-Gerasimenko for more than 2 years between 2014 and 2016, provided an unprecedented close-up portrait of a cometary nucleus, its strange bilobed shape, its rugged terrain of cliffs and boulders, its active surface venting jets of gas and dust, its chemical composition revealing a mixture of water, ice, carbon dioxide, carbon monoxide, formaldehyde, methanol, and dozens of complex organic molecules, including the amino acid glycine. The data returned by Rosetta transformed our understanding of comets not just as wandering visitors but as time capsules preserve fragments of the chemistry from which life itself may have emerged, or been seeded, or been inspired. Every comet we had ever studied told us something about the early solar system. Every comet was, in a sense, a message from our own past. And then, quietly, without any warning, without any precedent in the entire recorded history of astronomy, something arrived that was not from our past at all, something that carried a message from somewhere else entirely, something whose orbit, when calculated with careful and rigorous mathematics, described a hyperbolic trajectory, not a closed ellipse, not a parabola sitting at the boundary between bound and unbound, but a genuine hyperbola, a curve that enters the solar system from interstellar space and, after swinging around the sun, exits again on the other side, never to return. An object moving too fast, an object with too much energy, an object that did not belong to the sun's gravitational family and had never belonged to it, passing through our neighborhood the way a traveler passes through a town they have never visited and will never visit again, leaving only the faintest trace of their passage in the instruments of those paying close enough attention. The object was designated 2I Borisov. The 2I indicates that it was the second interstellar object ever confirmed. The Borisov honors the amateur astronomer Gennady Borisov, who discovered it on the 30th of August 2019 using a telescope he had built himself at the Crimean Astrophysical Observatory. Borisov was scanning the sky that morning as he often did, methodically sweeping through regions of the sky with the practiced patience of someone who has spent years looking without expecting to find anything remarkable, and yet always looking anyway, because that is the nature of the dedicated observer, the willingness to search without guarantee of discovery, to give the sky the gift of sustained attention and wait for the sky to respond. And on that particular morning, the sky responded with something extraordinary. Among the faint smudges and point sources of light in his field of view, there was something that moved differently, something whose brightness and color and the subtle extended appearance of its image suggested a comet, but whose position, when checked against catalogs of known solar system objects, returned no match. It was new, it was unknown, and when the initial orbital calculations were run cautiously at first, then with growing certainty as more observations came in from telescopes around the world, the conclusion was unmistakable. This was not one of ours. The first interstellar object had been discovered just 2 years earlier, in October 2017, by astronomer Robert Warwick, using the Pan-STARRS telescope at Haleakala Observatory in Hawaii. That object, designated 1I, Oumuamua, a Hawaiian name meaning roughly scout or messenger from afar arriving first, had already passed its closest approach to the sun by the time it was discovered and was rapidly departing the solar system. The window for observation was brief, the data sparse, and the object's nature deeply puzzling. Oumuamua showed no cometary activity, no coma, no tail, no outgassing signatures, and yet its trajectory showed an anomalous acceleration that could not be explained by gravity alone. It was elongated, perhaps cigar-shaped, or perhaps flat like a pancake. The observations were consistent with either geometry. It tumbled, it was red, and it left the solar system accelerating in a way that gravity could not account for, leading to a cascade of hypotheses ranging from the mundane to the provocative. A fragment of nitrogen ice from a Pluto-like world, a hydrogen iceberg, a thin sheet of natural material pushed by solar radiation pressure, or in the most discussed, if least likely, framing an artifact of an extraterrestrial civilization. Oumuamua was mysterious in ways that resisted easy resolution, and that mystery lingered, and to some degree still lingers today. But 2I, Borisov was different. 2I Borisov was, in the most important sense, recognizable. Where Oumuamua had confounded expectation at every turn, Borisov arrived behaving almost exactly as astronomers expected a comet to behave, outgassing, developing a coma, trailing a tail of dust and gas, brightening as it approached the sun and fading as it receded, revealing through its spectrum a composition that felt familiar and yet arrived from somewhere impossibly far away. It was, in a phrase that became common in the scientific literature almost immediately after its discovery, a perfectly ordinary comet doing something completely extraordinary, passing through someone else's solar system on its way to somewhere else in the galaxy, and doing so in such a cooperative, well-behaved, spectroscopically legible manner that astronomers could actually study it, really study it, in ways that had been impossible with Oumuamua. And what they found when they studied it was both deeply reassuring and quietly profound, because it suggested something about the universe that we had suspected but never confirmed, that the chemistry of planetary formation, the raw ingredients of comets and clouds, and perhaps even life, might not be unique to our solar system, but might instead be threaded throughout the galaxy, carried from system to system on trajectories that span the interstellar dark, shared across distances that make the word distance feel almost philosophical. This is where the story of 2I Borisov truly begins, not at the moment of its discovery, not in the flash of Gennady Borisov's recognition as he reviewed his images on an August morning, but much earlier, in the slow, cold, patient mathematics of interstellar space, in the processes that created this object and set it in motion, in the forces that nudged it free of its home system and sent it drifting outward into the galaxy, where it traveled for how long? We can only estimate. Across what distances we can only approximate, until by the exquisite coincidence of orbital mechanics and astronomical timing, it arrived in our small corner of the Milky Way at precisely the moment when human beings had built telescopes sensitive enough to detect it, and were pointing those telescopes at the right part of the sky, and had developed the mathematical tools to recognize it for what it was. The universe is patient, but so, in the end, are we. To appreciate what 2I Borisov represented to the scientific community, not merely as a curiosity or an anomaly, but as a window into processes operating at the scale of the entire galaxy, it is necessary to spend some time with the question of origins. Where do comets come from, in the most fundamental sense? What chain of events, stretching back billions of years, produces a small, icy body and sets it wandering through the darkness? And what additional chain of events, what specific gravitational drama, what close encounter, what slow perturbation accumulated over millennia is required to strip that body free of its home system entirely and send it across the interstellar void? These are not simple questions, and the answers we have assembled over decades of observation and theoretical modeling are answers built from inference and probability rather than direct observation, assembled piece by careful piece. The way a historian reconstructs an ancient civilization from fragments of pottery and the faint traces of walls buried beneath the soil. We understand the broad outlines. The details remain, in many places, beautifully uncertain. The story of a comet's origin begins in the same place that all planetary stories begin, in the protoplanetary disk, the vast, flattened cloud of gas and dust that surrounds a newly formed star in the first few million years of its existence. Within this disk, solid particles collide and stick together, growing from microscopic grains into millimeter-sized aggregates, then into centimeter-sized pebbles, then into meter-sized boulders, and eventually, through a process that is still not fully understood in all its details, into the kilometer-scale bodies we call planetesimals. These planetesimals are the building blocks of planets, the raw material from which rocky worlds and gas giants and ice giants are assembled through the slow, violent, stochastic process of gravitational accumulation. But not all planetesimals are incorporated into planets. Many remain as fragments, scattered and perturbed by the gravitational influence of the growing planetary bodies around them, flung outward to the cold, distant reaches of their system where the sun's warmth cannot reach them, where they settle into long, slow orbits, preserving within their frozen interiors the chemistry of the disk from which they formed. In our own solar system, these scattered remnants populate the Kuiper Belt and the Oort Cloud. In other systems, the equivalent populations exist in analogous structures, cold reservoirs of icy bodies orbiting at the periphery of their star's gravitational reach, sleeping archives of ancient chemistry, patient and still in the interstellar cold. The process by which one of these bodies is ejected entirely from its home system, promoted from a bound orbit around its star to a free, unbound trajectory through interstellar space, can unfold through several mechanisms, each operating on different timescales and requiring different conditions. The most commonly discussed mechanism involves close gravitational encounters with large planets, particularly gas giants. In the early history of a planetary system, when the giant planets are still migrating, moving inward or outward, as they exchange angular momentum with the surrounding disk of gas and planetesimals, their gravitational influence sweeps through vast regions of the system, scattering smaller bodies with extraordinary efficiency. Jupiter, in our own solar system, is estimated to have ejected enormous numbers of planetesimals during its early migration, flinging them outward past Neptune and beyond, some into the Oort Cloud and some, those receiving the strongest gravitational kicks, entirely out of the solar system on hyperbolic trajectories. Simulations of this process suggest that for every body retained in the Oort Cloud, perhaps 100 were ejected entirely into interstellar space, a staggering number, implying that the galaxy is filled with wandering comets, the discarded building material of 1,000 planetary systems, drifting through the interstellar medium in numbers too vast to easily conceptualize. This theoretical prediction that interstellar comets should exist in enormous numbers was made long before any had been observed. Astronomers had calculated that if planetary systems routinely eject cometary material during their formation, and if those ejected bodies drift through the galaxy in proportion to the density of stars and systems in any given region, then our solar system should be occasionally visited by interstellar comets, passing through our neighborhood on hyperbolic orbits before disappearing again into the dark. The predicted rate of such visitors varied, depending on the assumptions made about how efficiently planetary systems eject material and how long such objects survive before being destroyed by collisions or other processes. But some estimates suggested that at any given time, there might be several interstellar comets within the orbit of Neptune, simply waiting to be found by telescopes sensitive enough to detect them. The problem was that no telescope had been sensitive enough or had been surveying enough sky with enough frequency to catch one. The comets were predicted to be there. We simply had not yet been able to see them. Oumuamua changed that, but in a way that raised more questions than it answered. Its discovery was fortuitous. It was found after its closest approach, already departing, and the window for observation was narrow. Its nature was ambiguous. Its behavior was strange. It inspired an enormous amount of theoretical work and a great deal of public fascination. But it did not give scientists a clean, clear, detailed look at an interstellar object in the way they needed. It was a glimpse, tantalizing and incomplete, of something that demanded a fuller view. Borisov provided that fuller view, not perfectly, not completely, but far more generously than Oumuamua had. It was discovered weeks before its closest approach to the Sun, giving astronomers time to organize observing campaigns to point the world's most powerful telescopes at it in a coordinated and systematic way to gather spectroscopic data and photometric data and imaging data and polarimetric data, and to build from all of that a portrait incomplete, yes, but scientifically rich of an object that had formed around another star and traveled across the interstellar dark to pass through our solar system in the autumn and winter of 2019. The orbital mechanics of Borisov were calculated with remarkable precision relatively quickly after its discovery, as observations accumulated from telescopes around the world, and as archival data was searched for pre-discovery detections. The orbit was unambiguously hyperbolic, with an eccentricity of approximately 3.36 far in excess of the value of one that marks the boundary between a bound and unbound orbit. For comparison, the most eccentric orbit ever observed for a solar system comet prior to 2017 was significantly less than 1.1. An eccentricity of 3.36 was not a measurement that left room for interpretation. This object came from outside the solar system, period. Its incoming velocity relative to the Sun, before it had been significantly accelerated by solar gravity, was approximately 32 kilometers per second, a velocity consistent with its origin in the local stellar neighborhood, suggesting that it had been drifting through interstellar space for a period of time long enough to have reached what astronomers call the local standard of rest, the average velocity of the stars in our region of the galaxy, tracing its trajectory backward through space and time. Astronomers calculated that it had come from the general direction of the constellation Cassiopeia, with its path suggesting an origin somewhere in the stellar neighborhood within a few tens of light-years of Earth, though pinpointing a specific parent star proved impossible with the available data and may always remain uncertain. What made the trajectory calculation particularly interesting was what it revealed about the object's past history. Unlike Oumuamua, whose incoming velocity was notably high relative to the local standard of rest, suggesting either a very ancient ejection from a distant system or some additional acceleration mechanism that had been acting on it, Borisov's velocity was more moderate, more consistent with a body that had been moving through the interstellar medium for perhaps millions or hundreds of millions of years, gradually settling into a velocity profile consistent with the average stellar population around it. This did not mean its journey had been short. Even at tens of kilometers per second, crossing interstellar distances requires millions or billions of years. But the velocity profile was compatible with a body that had formed in a system similar in age and galactic position to our own, been ejected during or after that system's planetary formation phase, and spent an enormously long time drifting through the interstellar medium before arriving in our neighborhood. It was old, in other words, in the way that things from the universe's deep past are old, not ancient in the cosmic sense of the early universe, but old in the quiet, patient, geological sense of something that has been moving through the dark for longer than complex life has existed on Earth. The discovery triggered an immediate and remarkable mobilization of the astronomical community. Within days of the confirmation of Borisov's interstellar nature, proposals for observing time on major telescopes were being drafted, reviewed, and approved with a speed unusual in an enterprise that is typically characterized by careful, deliberate timelines. The Hubble Space Telescope was pointed at it. The Very Large Telescope at the European Southern Observatory in Chile was directed toward it. The Gemini Observatory, the Keck Observatory, the Apache Point Observatory, and dozens of other facilities around the world began gathering data. Amateur astronomers with large telescopes tracked it across the sky, contributing their own photometric measurements to the growing dataset. There was a palpable sense of urgency, not panic, not excitement in the breathless, tabloid sense, but the quiet urgency of scientists who understand that an opportunity of this kind is extraordinarily rare, that the data available now might be the only data of its kind available for years or decades, and that every observation gathered during this window would contribute to a body of knowledge that could not be gathered any other way. You cannot send a spacecraft to an interstellar comet passing through at 32 kilometers per second on a hyperbolic trajectory with only weeks of notice. The physics of such a mission are, at present, entirely beyond our capability. The only way to study Borisov was with the telescopes we already had, pointed at the sky, gathering every photon it was willing to share with us before it disappeared forever beyond the edge of the solar system and back into the interstellar dark from which it had come. The portrait that emerged from all of this accumulated observation was, in its broad outlines, both comforting and wondrous in equal measure. Comforting because so much of what astronomers saw was familiar, and wondrous because the familiarity itself, arriving from across the interstellar void, carried within it an implication so large and so quietly staggering that it took time to fully absorb. The comet behaved like a comet. It outgassed. It developed a coma. It produced a tail. It brightened as it approached the sun and faded as it receded. The gases it released were identifiable, readable in the spectrograph's rainbow of absorbed and emitted light. And what those spectrographs read was something that any planetary scientist studying comets in our own solar system would have recognized immediately. Carbon monoxide, water, the fingerprints of chemistry that we had seen in comet after comet from our own Oort Cloud and Kuiper Belt. chemistry assembled from the same basic molecular building blocks, shaped by the same fundamental physics of ice sublimation and photodissociation, readable in the same spectral lines that had been cataloged and studied for decades in the comets of our own solar neighborhood. It was, in the most profound and quietly beautiful sense, familiar. And in that familiarity was the suggestion of something enormous, that the chemistry of comets, and perhaps the chemistry of life's precursors, might be not a local accident but a universal tendency, written into the physics and chemistry of planetary formation wherever in the galaxy that formation occurs, carried from system to system on the slow currents of the interstellar medium, connecting worlds that will never otherwise communicate, across distances that will never otherwise be crossed. There is a particular kind of scientific moment that does not announce itself with fanfare, that arrives instead in the quiet accumulation of data, in the slow convergence of measurements taken from different instruments on different nights by different teams of researchers, each adding a small piece to a picture that only becomes visible when you step back far enough to see the whole. The study of 2I, Borisov, was filled with such moments, and perhaps the most important of them came when astronomers began to look seriously at the comet's chemical composition, not just at the broad outlines of what gases it was releasing, but at the specific ratios, the relative abundances, the precise molecular fingerprints that could be compared against the accumulated database of measurements taken from comets in our own solar system over decades of careful observation. Because it is in these details, in the specific proportions of one molecule to another, in the ratios that reflect not just what a comet is made of, but how and where and under what conditions it formed, that the most profound information is encoded. A comet is not just a lump of ice and dust. It is a record, a chemical diary written in the language of molecular bonds and isotopic ratios, preserving in its frozen heart the conditions that prevailed in the protoplanetary disk where it was born, the temperature gradients and pressure profiles, and elemental abundances of a system that may be tens of light years away and completely inaccessible to us by any other means. The first spectroscopic detections of gas around 2I, Borisov, came within days of its confirmation as an interstellar object. A team led by Alan Fitzsimmons at Queen's University Belfast detected the presence of cyanogen, the CN radical, a fragment produced when hydrogen cyanide and other complex molecules are broken apart by ultraviolet radiation from the sun in the comet's coma. This was significant for several reasons, not least because CN is one of the most commonly detected molecules in cometary Comet, and its presence in Borisov immediately placed this interstellar visitor in the same general chemical family as the comets of our own solar system. The CN detection was followed quickly by measurements of other species, diatomic carbon, atomic oxygen, and eventually water itself, detected through its photodissociation products, including the hydroxyl radical OH. Each detection added another line to the chemical portrait, and each line, when compared against the spectral catalogs built up from decades of studying solar system comets, told the same quiet story. This object, formed around a different star, perhaps in a different part of the galaxy, perhaps billions of years ago, was made of recognizably similar stuff. But the measurement that generated perhaps the most scientific attention and the most careful follow-up work was the detection of carbon monoxide, CO, in the coma of 2I, Borisov. This detection was reported in two independent papers, published nearly simultaneously in the journal Nature Astronomy in early 2020, one from a team led by Dennis Bodowitz at Auburn University using the Hubble Space Telescope, and another from a team led by Martin Cordner at NASA's Goddard Space Flight Center using the Atacama Large Millimeter Array in Chile. Both teams found carbon monoxide in the comet's coma, and both found it in quantities that were, by the standards of solar system comets, remarkably high, significantly elevated relative to the water production rate that was being measured simultaneously. In solar system comets, CO-to-water ratios vary considerably, but the ratio measured in Borisov placed it at the high end of the distribution, comparable to comets like C. 2016 R2, Pan-STARRS, an unusual solar system comet that is itself thought to have formed in the outer reaches of the solar system, where temperatures are low enough to preserve CO ice in large quantities. This comparison was telling. The high CO abundance in Borisov suggested that it had formed in the cold outer regions of its home system far from its parent star, in a region cold enough to have trapped large quantities of CO in its ices, and that it had spent much of its subsequent history in conditions cold enough to preserve those volatile ices against the slow erosion of cosmic rays. Interstellar radiation. It was a cold body, in the deepest sense shaped by cold, preserved by cold, and carrying within its frozen heart the chemical signature of the cold outer dark of another planetary system. The significance of the CO detection extended beyond the simple fact of its presence. Carbon monoxide is a particularly volatile ice. It sublimates at temperatures far lower than water ice, making it one of the first ices to be released when a comet approaches a heat source and one of the most sensitive indicators of the thermal environment in which a comet formed. In our own solar system, the distribution of CO in comets reflects their formation locations within the protoplanetary disk comets that formed closer to the Sun processed more heat and lost their CO during formation, while comets that formed in the cold outer reaches retained it. By analogy, the high CO content of 2I Borisov implied a formation location in the cold outer regions of its home system, beyond whatever equivalent of Neptune or Uranus that system possessed, in a region where the temperature dropped below the sublimation point of CO, and where this volatile molecule could be incorporated into the growing icy body rather than simply evaporating away. This was a physically meaningful constraint on the comet's formation environment, not just a description of what it contained, but an inference about where in its home system it had formed, based on the same thermodynamic principles that govern cometary chemistry everywhere in the galaxy. Beyond the carbon monoxide, the water production rate of 2I Borisov was measured and tracked as the comet approached and then receded from the Sun. Water ice is the dominant volatile in most comets, and the rate at which water is released from a cometary nucleus, its water production rate, provides a measure of both the size of the active sublimating surface and the fraction of the nucleus that is covered by water ice rather than insulating dust. In Borisov, the water production rate was consistent with a nucleus of modest size estimates based on the outgassing rate, and assumptions about the active fraction of the surface suggested a nucleus somewhere in the range of half a kilometer, a kilometer in diameter, placing it in the same size range as many well-studied solar system comets. The nucleus itself proved difficult to image directly. Even the Hubble Space Telescope could not resolve it against the bright background of the surrounding coma, but indirect estimates based on the reflected light from the coma and the measured outgassing rates were consistent with a relatively small, moderately active body, unremarkable in its physical dimensions, but extraordinary in its provenance. The dust released by 2I Borisov was also studied in considerable detail, and here again the findings were simultaneously reassuring and quietly remarkable. The properties of the dust, its scattering behavior as measured through photometric observations at different wavelengths, its polarization behavior as measured by specialized instruments designed to detect the polarization of light scattered by small particles, its color as measured through broadband filters, were all consistent with the properties of dust observed in solar system comets. The dust particles appeared to be composed of silicate and carbonaceous materials, similar in their optical properties to the dust seen in comets like Halley, Hale-Bopp, and the targets of the Stardust mission. The color of the dust was in the range typical for solar system cometary dust, slightly reddish, as is common for processed organic material in space, but not dramatically red in the way that some outer solar system bodies are, and not unusually blue in the way that would suggest a composition dominated by freshwater ice. It was, in every measurable way, cometary dust, the same kind of material that a solar system comet would shed as it warmed near the Sun, the same kind of material that had been collected and analyzed in the laboratory from Comet Wild 2 by the Stardust spacecraft, and found to contain a surprising diversity of crystalline silicates and organic compounds. The dust of 2I Borisov, arriving from another star, looked like the dust of our own comets. And this similarity, this quiet echo of familiarity across the interstellar void, was perhaps the deepest and most resonant finding of all. There was one additional observation of 2I Borisov that deserves particular attention, not because it was unexpected, but because of the timing and circumstance in which it was made, and the brief fragile drama it introduced into what had otherwise been a story of reassuring chemical familiarity. In late March 2020, as the comet was already well past its closest approach to the Sun and beginning its long journey back into the interstellar dark, a team of astronomers using the Hubble Space Telescope reported something unusual in the comet's appearance. The nucleus appeared to have undergone a fragmentation event, a partial breakup, the kind of structural disruption that is seen occasionally in solar system comets when thermal stresses or tidal forces or simply the mechanical weakness of a loosely consolidated icy body cause it to crack, to split, to shed fragments that then drift away from the main nucleus on slightly different trajectories, forming a train of small pieces that can be tracked for days or weeks before they fade beyond detection. The evidence for fragmentation in 2I Borisov was not dramatic. There was no sudden, spectacular splitting into two clearly resolved pieces, as had been seen in comets like Shoemaker-Levy 9 when it broke apart under Jupiter's tidal forces in 1992, or in Comet 73P, Schwarzmann-Wachmann 3, which fragmented into dozens of pieces over the course of several apparitions. What was seen in Borisov was subtler, a broadening and brightening of the central condensation of the coma, an elongation of the inner coma profile that suggested the presence of additional material recently shed from the nucleus, a slight asymmetry in the coma's brightness distribution that was difficult to explain without invoking some structural change in the nucleus itself. The fragmentation, if that is what it was consistent with what might be expected from a comet making its first passage close to a star, perhaps the first such passage in billions of years, if the object had spent most of its existence in the cold interstellar dark at temperatures close to the background radiation temperature of the universe, around 2.7 Kelvin, where no thermal cycling could weaken its structure, where no periodic outgassing could create voids or fractures in its interior. A comet from our own Oort Cloud, making its first passage through the inner solar system, is also thought to be structurally pristine. Never having experienced the thermal stresses of solar heating, it has not developed the layered structure of outgassing residues and dust mantles that longer-period comets accumulate over repeated perihelion passages. And it can be more volatile-rich, more structurally fragile, more prone to outbursts and fragmentation than a comet that has passed through the inner solar system many times and been gradually processed by the experience. By this analogy, 2I Borisov, if it had truly never previously passed close to any star since its ejection from its home system, would be in a similarly pristine and structurally untested state, rich in volatiles preserved by billions of years of cold storage, but perhaps mechanically fragile, unaccustomed to the thermal and rotational stresses that solar heating imposes. The fragmentation hints were, in this light, not surprising. They were, if anything, consistent with the picture of an ancient, pristine, volatile-rich body encountering real stellar warmth perhaps for the first time since its formation. The comet continued to move outward through the solar system through the spring and summer of 2020, fading steadily as it receded from both the Sun and the Earth. The last observations from large ground-based telescopes tracking it until it faded below the threshold of detectability, sometime in mid-2020, leaving behind only the data it had generated during its brief passage: terabytes of images, spectra, polarimetric measurements, photometric light curves, all preserved in the archives of the telescopes that had watched it, waiting for the continued analysis that would take months and years to complete. It was gone before we were done with it, as the most important visitors often are, departing before all the questions they prompted could be answered, leaving us to work with what they had given us and to carry the questions they had left unanswered forward into the future, into the next instrument, the next survey, the next discovery that might shed additional light on what they had revealed. There is something deeply human about the way we respond to the departure of something extraordinary, the way the mind continues to work on a problem even after the object of its attention has moved beyond reach, the way questions multiply in the wake of an encounter rather than diminishing, the way the absence of something remarkable becomes its own kind of presence, filling the space where certainty used to be with the more fertile and more honest substance of continued inquiry. The astronomers who had spent months watching 2I Borisov cross their fields of view, who had gathered its light in their spectrographs, and parsed its chemistry from the scattered photons it offered them, did not stop thinking about it when it faded below the threshold of detection in the summer of 2020. They continued to work with the data it had left behind, publishing papers through 2020 and 2021 and beyond, each paper adding another facet to the portrait, refining the estimates, narrowing the uncertainties, building toward a more complete understanding of what this object had been, where it had come from, and what its existence implied about the broader universe, of which our solar system is only the smallest, most local part. The science of 2I, Borisov, did not end with the comet's departure. In many ways, it was only beginning. One of the most carefully studied aspects of the comet in the months following its discovery was its dust, not just the bulk properties of the dust coma, as measured through broadband photometry, but the detailed microphysical properties of the individual dust particles themselves, as inferred from the way they scattered and polarized sunlight at different angles and wavelengths. Polarimetry is a technique that has been applied to solar system comets for decades and has proven to be an exquisitely sensitive probe of dust particle properties, their size, distribution, their composition, their porosity, and the degree to which they are aggregated into complex, fluffy structures, rather than being compact, solid grains. The polarimetric behavior of a comet's dust changes systematically as the angle between the Sun, the comet, and the observer changes, tracing out a characteristic curve that reflects the optical properties of the scattering particles in ways that can be compared against laboratory measurements of known materials and against theoretical models of light scattering by particles of various shapes and compositions. By fitting the observed polarimetric curve of a comet's coma to these models and measurements, astronomers can build up a picture of what the dust particles are like, even though they are far too small and far too distant to be imaged directly. For 2I, Borisov, polarimetric measurements were made by several independent groups using telescopes in different parts of the world, and the results, when compared against the extensive database of polarimetric measurements compiled for solar system comets over many decades, were striking in their consistency with the solar system norm. The polarimetric behavior of Borisov's dust fell well within the range observed for solar system comets, specifically within the range associated with comets that have moderately active surfaces and dust populations dominated by porous, aggregate particles composed of silicate and carbonaceous material. This placed Borisov in a familiar optical category, distinguishing it clearly from other classes of solar systems, small bodies, asteroids, for example, or the highly processed nuclei of comets that have made many perihelion passages and developed thick dust mantles, and aligning it instead with the population of relatively pristine, actively outgassing comets that represent the less processed end of the solar system cometary population. The dust of 2I, Borisov, in other words, looked and behaved like the dust of a fresh, relatively unprocessed solar system comet, suggesting that the physical processes governing the structure and properties of cometary dust, the aggregation of small grains into porous, fluffy particles, the coating of silicate cores with organic mantles, the formation of complex hierarchical structures through low-velocity collisions in the protoplanetary disk, operate in similar ways around other stars, producing particles with similar microphysical properties to those found in our own solar system's comets. This finding carried implications that extended well beyond the immediate question of what 2I, Borisov, was made of. The formation of dust particles in protoplanetary disks is a problem of fundamental importance to planetary science. Understanding how grains stick together, how they grow from microscopic sizes to the pebble and boulder scales where gravity begins to play a significant role, and what determines the final size distribution and composition of the solid material in a forming planetary system, are all questions at the heart of the theory of planet formation. The fact that 2I, Borisov's dust, appeared to have similar microphysical properties to the dust in solar system comets suggested that the dust evolution processes operating in its home system's protoplanetary disk were not dramatically different from those that operated in our own solar nebula, that the same basic physics of grain-grain collisions, surface energy, and electrostatic forces that drove dust aggregation in the disk around our young sun was also operating in whatever disk surrounded the star that gave birth to Borisov. This was a confirmation, indirect but meaningful, of the universality of dust physics, a suggestion that the rules governing the smallest scale of planetary formation are the same everywhere in the galaxy, producing similar raw materials from which planetary systems of all kinds can be assembled. The water in 2I. Borisov also told a story worth listening to carefully. Water is the dominant volatile in the vast majority of solar system comets, and its presence in 2I. Borisov detected through the hydroxyl radical OH, a photodissociation product of water that emits at ultraviolet wavelengths and is one of the standard diagnostic tools for measuring water production in comets, was both expected and significant. Water ice forms at temperatures below 273 Kelvin and is thought to be the dominant reservoir of oxygen in the outer regions of protoplanetary disks, beyond the so-called snow line, the distance from a forming star at which the temperature drops low enough for water vapor to condense into ice. The location of the snow line in a protoplanetary disk depends on the luminosity of the central star and on the density and structure of the disk itself. But in a general sense, it represents a fundamental boundary in the chemistry of planet formation. Inside the snow line, water exists primarily as vapor and is not available to be incorporated into solid bodies. While outside it, water ice is abundant and becomes one of the primary building materials of icy planetesimals and ultimately comets. The presence of abundant water ice in 2I, Borisov implied that it had formed outside the snow line of its home system, a constraint consistent with the comet's high CO abundance. Since the two lines of evidence pointed toward formation in the cold outer regions of a protoplanetary disk where both water and carbon monoxide could be preserved in solid form. The specific ratio of carbon monoxide to water in 2I, Borisov, was a particularly informative number, and its interpretation required care and nuance. In solar system comets, coal-to-water ratios span a wide range from less than 1% to more than 20% by number, reflecting the diversity of formation environments within the solar system's protoplanetary disk, the diversity of subsequent dynamical histories, and the varying degrees of thermal processing that different comets have experienced during their lifetimes. The ratio measured in Borisov, which both the Hubble team and the ALMA team independently placed at roughly 35% or higher during the period of peak activity, was at the extreme high end of this range, comparable to only the most CO-rich solar system comets. As noted in Part 2, the closest solar system analog was C 2016R, 2 Pan-STARRS, a remarkable comet that had itself been the subject of considerable scientific attention because of its unusually high CO abundance, which was accompanied by an unusual absence of the typical water-driven activity that characterizes most comets, and which suggested a formation environment or subsequent thermal history very different from that of typical solar system comets. The comparison between Borisov and C 2016 R2 raised interesting questions. Were both objects representative of a class of co-rich cometary bodies that form preferentially in the cold outer regions of planetary systems? Or was the similarity a coincidence, reflecting the fact that both objects happened to be observed during a period of particularly active CO outgassing that might not be representative of their bulk compositions? These questions could not be fully resolved from the available data, but they pointed toward the importance of continuing to study CO-rich comets in our own solar system as analogs for interstellar visitors. Beyond the chemistry, the physical behavior of 2I, Borisov, as it passed through the solar system, offered additional clues to its nature and history. The comet's activity level, the rate at which it was releasing gas and dust, was tracked continuously from the time of discovery through the end of its detectability, and the light curve that emerged from this tracking revealed a body that was active, but not dramatically so, brightening gradually as it approached the sun and fading gradually as it receded, without the sudden outburst or dramatic brightness changes that are sometimes seen in solar system comets undergoing rapid sublimation of highly volatile species or structural disruptions of their nuclei. There was the fragmentation evidence noted in Part 3. Subtle and suggestive rather than dramatic and conclusive. But aside from that episode, the overall behavior of the comet was regular and well behaved. The behavior of a body whose outgassing was driven primarily by water, ice sublimation in the inner coma, and CO sublimation. From deeper within the nucleus, both processes proceeding in the orderly, predictable manner that cometary physicists have come to expect from a moderately active comet with a reasonably uniform surface distribution of active areas. The rotation of the nucleus was another parameter that astronomers attempted to measure, though with only limited success given the impossibility of resolving the nucleus directly, even with the best available telescopes. Rotation rates in comets are important because they influence the pattern of outgassing. A rotating nucleus alternately exposes different surface regions to sunlight, causing asymmetric jets of gas and dust that can in turn exert torques on the nucleus and change its rotation rate over time. In Oumuamua, the rotation had been inferred from the periodic brightness variations of the bare nucleus. No coma was present to obscure the signal and had been found to be complex and potentially in an excited, tumbling state. For 2I Borisov, the presence of a coma made direct rotation measurements much harder, since the extended emission from the coma diluted and blurred any periodic variations in the light from the nucleus itself. Several teams attempted to extract rotation periods from careful photometric monitoring, and some reported tentative periods in the range of several hours to about a day, but these measurements were acknowledged to be uncertain and not fully consistent across different datasets. What could be said with confidence was that the nucleus was not rotating catastrophically fast. It had not been spun up to the breakup limit by asymmetric outgassing torques, which would have been evident from the rate of material loss, and that whatever its rotation state, it was broadly consistent with the range of rotation rates observed in solar system comets of comparable size. The combination of all these measurements, the chemistry, the dust properties, the water and CO production rates, the activity level, the fragmentation hints, the inferred nucleus size and rotation painted a picture of 2I Borisov as a comet that was, in its essential nature, very much like the comets of our own solar system, while simultaneously being, in its origin and its history, something entirely unprecedented in the record of human astronomical observation. It had formed around another star. It had spent an unimaginable length of time in the cold interstellar dark between the stars. It had arrived in our solar system, carrying within its frozen core the chemistry of a planetary system we will never visit. And it had shared that chemistry with us as freely and as openly as any comet ever has, releasing its gases into the sunlight, scattering its dust across the sky, offering its molecular fingerprints to our spectrographs, with the same patient generosity that the universe always shows to those who are patient enough and attentive enough to receive what it offers. And then it had departed, as quietly and as inevitably as it had arrived, leaving us with data and questions and the slowly growing understanding that the universe is, in its chemistry at least, more coherent and more unified than we had dared to fully believe before this small, cold, ancient traveler passed through our neighborhood and showed us what it was made of. To sit with the implications of 2I Borisov's chemical familiarity, to really sit with them in the way that good science requires, not rushing past the surface of the finding toward the next measurement or the next paper, but pausing instead in the space that the finding opens up, is to find yourself drawn into a question that is at once deeply technical, deeply philosophical, a question about the nature of chemistry itself and about the degree to which the universe can be said to have preferences, tendencies, default states toward which it gravitates when left to its own devices across the vast scales of space and time that constitute the cosmic arena. The question, put simply, is this: is the chemistry we see in comets, the water ice, the carbon monoxide, the complex organic molecules, the silicate dust, a universal outcome of the physics of planetary formation, something that will arise wherever a protoplanetary disk cools and condenses around a newly formed star? Or is it instead a local peculiarity of our own solar system, a specific chemical configuration that happened to emerge from the particular conditions of our particular corner of the galaxy and might look very different in other systems around other stars? Before 2I Borisov, this question was entirely open. After 2I Borisov, it was not closed. Science rarely closes questions so definitively from a single observation, but it was tilted. meaningfully and measurably toward the answer that the chemistry of comets is indeed something like a universal outcome, a predictable product of the physics and chemistry of disk evolution that arises not just here, but in general, wherever the conditions are broadly similar to those that prevailed in our own young solar system. This tilting of the evidential balance has implications that extend far beyond the specific question of cometary chemistry. Because comets are not just interesting in themselves, they are interesting for what they may have contributed to the conditions that allowed life to arise on Earth. This connection between comets and life is one of the most actively debated topics in astrobiology, and it has a long and contentious history that is worth exploring in some depth here because it provides the broader context within which the significance of 2I, Borisov's chemistry, can be most fully appreciated. The hypothesis, in its most general form, is that comets and to a lesser extent asteroids delivered to the early Earth significant quantities of water, organic molecules, and perhaps other biologically important materials during a period of intense bombardment in the early solar system, and that these delivered materials contributed in important ways to the conditions that eventually permitted life to emerge. This hypothesis goes by various names: panspermia, in its most extreme form, where actual living organisms or their direct precursors are proposed to have been delivered from space, and the more widely accepted delivery hypothesis, or exogenous delivery hypothesis, in its more modest form, where it is the chemical raw materials of life, the water, the carbon compounds, the nitrogen-bearing molecules, rather than life itself, that are proposed to have been delivered. The evidence for and against these ideas is complex and sometimes contradictory, and the scientific community remains divided on the relative importance of exogenous delivery versus in situ synthesis of biologically important molecules on the early Earth, but the debate itself underscores the deep connection between the chemistry of comets and the question of life's origins that makes the study of cometary composition so much more than an exercise in planetary science. The organic chemistry preserved in comets is remarkably rich. Observations of solar system comets from the ground, from space, and most dramatically from the in situ measurements made by the Rosetta mission at Comet 67P, have revealed a bewildering variety of organic molecules, ranging from simple species like formaldehyde and methanol, through more complex molecules like ethanol, glycolaldehyde, and even the amino acid glycine. The detection of glycine in the coma of 67P by the Rosetta mass spectrometer was particularly significant, because glycine is the simplest amino acid, and amino acids are the building blocks of proteins, which are in turn essential components of all known life. The presence of glycine in a comet, a molecule that can only form through specific chemical reactions that require both carbon, nitrogen, and hydrogen in the right configurations, demonstrated that comets can harbor molecules of direct biological relevance, molecules that exist at the chemical frontier between the inanimate universe and the living world. And glycine is not alone. The suite of organic molecules detected in comets includes molecules that are relevant to the chemistry of nucleotides, the building blocks of DNA and RNA, and to the formation of lipid-like molecules that could self-assemble into primitive membranes, the structural envelopes within which the chemistry of life is organized and protected. Comets are, in a very real chemical sense, extraordinarily well stocked with the raw materials of life. The question of whether these materials were delivered to the early Earth in significant quantities during the period known as the Late Heavy Bombardment, a period roughly 3.8 to 4.1 billion years ago when the inner solar system experienced an elevated flux of impactors, possibly related to a dynamical instability in the orbits of the giant planets, is a question about both the total mass of cometary material that struck the Earth during that period and the survivability of organic molecules through the violence of a cometary impact. Impact simulations suggest that a significant fraction of the organic material carried by a comet can survive the impact event if the impactor is small enough and the impact angle is shallow enough, preserved in the form of shock-processed but still chemically complex residues that are dispersed across the impact site and incorporated into the surrounding geology. Laboratory experiments simulating cometary impacts at various velocities and angles have confirmed that organics can survive, even if they are chemically modified in the process, The products of cometary impacts are not identical to the incoming material, but they retain much of the chemical complexity and biological relevance of the precursor molecules. This survivability, combined with the enormous quantities of cometary material that struck the early Earth during the Late Heavy Bombardment, has led many astrobiologists to conclude that the contribution of cometary organics to the prebiotic chemistry of the early Earth was at minimum non-negligible and quite possibly significant. Now, consider what it means in this context to have confirmed that an interstellar comet carries chemistry broadly similar to that of solar system comets. If the chemistry of 2I, Borisov, its water ice, its carbon monoxide, its CN-bearing molecules, its silicate dust with organic mantles, is representative of the chemistry of comets around other stars in general, then the implication is that the raw materials for prebiotic chemistry are not confined to our solar system, but are distributed throughout the galaxy, carried by comets that form around star after star and are then ejected into interstellar space in vast numbers during the planetary formation process. These interstellar comets, billions upon billions of them, drifting through the galaxy over timescales of billions of years, could in principle deliver organic chemistry to any planetary system they happen to pass through, provided that some fraction of them impact planets' inhabitable zones rather than simply passing through on their hyperbolic trajectories and departing again. The probability of any individual interstellar comet impacting a specific planet is vanishingly small. The solar system is almost incomprehensibly empty, and the chances of a randomly directed interstellar visitor happening to intersect the orbit of a specific planet are extraordinarily low. But across cosmic timescales and across the enormous numbers of interstellar comets that must be drifting through the galaxy, even vanishingly small probabilities can add up to meaningful event rates. It is at least possible, perhaps even probable, in the view of some astrobiologists, that interstellar comets have delivered organic chemistry to habitable planets around stars throughout the galaxy, connecting the chemistry of different planetary systems in ways that operate on timescales too long for any individual civilization to observe, but that are nonetheless real and consequential at the level of galactic chemical evolution. This vision of the galaxy as a chemically connected ecosystem, with interstellar comets serving as the slow, patient messengers carrying organic chemistry from system to system across the interstellar dark, is one that resonates deeply with the broader picture of cosmic chemical evolution that has emerged from decades of astronomical observation. We know that the heavy elements, the carbon, nitrogen, oxygen, silicon, iron, and all the other atoms that make up planets and life are produced in the nuclear furnaces of stars and distributed through the galaxy by stellar winds and supernova explosions, enriching the interstellar medium over time in a process of progressive chemical complexity that has been ongoing since the first generation of stars ignited in the early universe. We know that the interstellar medium itself is chemically rich. Radio observations have detected more than 200 distinct molecular species in interstellar clouds, including complex organic molecules like glycolaldehyde, acetone, and even the simplest sugar alcohol, ethylene glycol. And we know that the chemistry of interstellar clouds is incorporated into protoplanetary disks when those clouds collapse to form new stars and planetary systems. The chemistry of the universe is not static. It evolves. It grows more complex over time, passed from generation to generation of stars, carried from environment to environment by the physical processes of stellar evolution and planetary formation. And perhaps if interstellar comets play the role that 2I, Borisov suggests, they might carried also from system to system by these small, cold, ancient travelers drifting through the interstellar dark. In this context, the detection of oxygen in 2I, Borisov reported by a team of researchers analyzing archival spectra of the comet, with particular attention to the emission lines of atomic oxygen that are produced when water, carbon dioxide, and other oxygen-bearing molecules are broken apart by solar ultraviolet radiation, added another layer of chemical richness to the portrait. Atomic oxygen in cometary Comet is not unusual in itself, It is a standard photodissociation product of the most common cometary volatiles, but the specific ratio of singlet D oxygen emission to singlet S oxygen emission, which encodes information about the relative contributions of water, CO2, and CO to the oxygen budget of the coma, provided an additional constraint on the volatile composition of the nucleus that was consistent with the picture emerging from the CO and water measurements. A nucleus rich in both water ice and CO ice, with CO2 likely present as well, forming a chemical inventory that placed Borisov firmly in the category of volatile-rich outer disk comets, both in our own solar system and, by extension, in whatever system had given birth to it. The months following 2I, Borisov's departure from the solar system saw a steady stream of papers continuing to refine and extend the analysis of the data gathered during its passage papers, examining the fine structure of the dust coma in Hubble images, papers modeling the outgassing behavior from different regions of the nucleus, papers using ALMA's millimeter wave sensitivity to search for additional molecular species in the coma, papers comparing the polarimetric properties of the dust against laboratory measurements of candidate materials. Each paper added a small but real increment to the understanding of this object, and collectively they built a scientific literature on 2I. Borisov that, while necessarily incomplete, every paper acknowledged the limitations imposed by the brevity of the observational window, and the impossibility of in situ measurement was, nevertheless, a genuinely substantial body of knowledge about an object from another star, assembled in the space of a single apparition, through the combined efforts of dozens of research groups around the world, working with the tools they had rather than the tools they wished they had. It was, in many ways, a model of what planetary science can accomplish when an extraordinary discovery focuses the community's attention and resources on a single target with a sense of shared purpose and genuine scientific urgency, when the temporary boundaries between research groups and telescope committees and institutional priorities soften in the face of something that matters to all of them equally, and that none of them can fully address alone. The legacy of these papers, the scientific literature they collectively constitute, is not merely the sum of the specific measurements they report. It is also, and perhaps more importantly, a demonstration of what is possible, that a comet from another star can be found, studied, characterized in meaningful detail, and understood well enough to draw scientifically defensible conclusions about its origin, its composition, and its implications, all within the span of a single observational season, using existing telescopes and existing analytical techniques. This demonstration matters because the next interstellar object, whatever it turns out to be, whenever it arrives, will be studied in a context shaped by what was learned from Borisov, with hypotheses already formed, with comparison datasets already assembled, with the community already primed by experience to extract maximum scientific value from whatever window of observation becomes available. Science is cumulative in this way. Each discovery changes not just what we know, but how we look. Not just the answers we have, but the questions we know how to ask. And in this sense, the legacy of 2I, Borisov, extends far beyond the specific facts it revealed about itself into the future of a field that it helped to create simply by existing and by being found at the moment when we were ready, just barely, to find it. There is a discipline within astronomy that concerns itself not with the objects that have been found, but with the objects that have not yet been found, not with the known population of comets and asteroids and interstellar visitors that have passed through our telescope's fields of view and left their chemical signatures in our spectrographs, but with the much larger, much more uncertain population that must exist based on statistical arguments and theoretical models, the vast invisible majority of which we have so far detected only the most tentative and preliminary fraction. This discipline, the statistical characterization of populations from small samples, the inference of the whole from the part, the estimation of what must be out there based on what has so far been seen, is one of the most intellectually demanding and epistemologically subtle areas of observational science, requiring a careful and constant awareness of the biases and limitations built into any observational survey, the ways in which the instruments we use and the strategies we employ to search the sky systematically favor the detection of some objects over others and thereby distort the sample we collect in ways that must be corrected for before any population-level conclusions can be drawn. In the case of interstellar objects, the population to which both Oumuamua and Borisov belong. This statistical discipline has been particularly active in the years following the discovery of those two objects, as astronomers have worked to estimate from the two confirmed detections how many interstellar objects must be passing through the solar system at any given time, and what that number implies about the rate at which other planetary systems shed material into interstellar space. The calculation, in its broad outlines, begins with the observational facts. Two interstellar objects were detected in the span of roughly 2 years, between October 2017 and August 2019, by surveys with known detection thresholds and known sky coverage rates. From these facts, combined with models of how the detection efficiency of a given survey depends on the size, brightness, and velocity of the objects it is searching for, it is possible to estimate the number density of interstellar objects in the solar neighborhood, that is, how many such objects exist per unit volume of space in the region around our Sun. The estimates that have been published based on the Oumuamua and Borisov detections span a fairly wide range, reflecting the significant uncertainties involved, but they consistently point to a number density that is, in the words of several papers, surprisingly high, much higher than pre-discovery theoretical estimates had suggested, and high enough to imply that interstellar objects are not rare vagrants passing through our solar system once in a geological age, but rather a continuous and significant component of the solar neighborhood's small body population, with perhaps several interstellar objects inside the orbit of Neptune at any given time, and with our solar system experiencing something like one interstellar visitor per year that is large enough and bright enough to be detectable by a sufficiently capable survey. The implications of this high number density are remarkable. If interstellar objects are as common as the Oumuamua and Borisov detections suggest, then the total mass of material being exchanged between planetary systems across the galaxy, carried on the slow currents of interstellar space by ejected comets and asteroids, and whatever other categories of interstellar small body exist, is very large indeed. Estimates of the total mass flux of interstellar cometary material through the solar neighborhood, derived from the inferred number density and the assumed size distribution of the population, suggest that the solar system is being continually bathed in a slow rain of interstellar material, tiny in any individual piece but enormous in aggregate over geological timescales. This material, these fragments of other planetary systems, carrying the chemistry of their origin environments, is not merely passing through. Some small fraction of it must be captured into bound solar system orbits by gravitational interactions with the planets, particularly Jupiter, becoming temporarily or permanently incorporated into the solar system's own small body population. Some fraction may ultimately impact the planets themselves, delivering their chemical cargo to planetary surfaces in the same way that solar system comets are thought to have delivered water and organics to the early Earth. The solar system is not a closed system. It has never been a closed system. It is embedded in a galaxy that is chemically and dynamically connected at every scale, and the interstellar objects passing through it are one of the physical mechanisms through which that connectivity manifests at the local level. The statistical estimates derived from the Oumuamua and Borisov detections also have important implications for the design and capabilities of future sky surveys, because they define the expected rate at which interstellar objects should be detectable by surveys of various depths and sky coverage rates. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, or LSST, which began its legacy survey of space and time in the mid-2020s, is expected to be transformative in this context. The Rubin Observatory is designed to survey the entire visible sky repeatedly, with a cadence of roughly 3 days per visit to any given sky position, using an 8.4-meter primary mirror and a 3.2 gigapixel camera to reach faint limiting magnitudes across a wide field of view.